is it 6.5 now? Oh, this is kind of like the end of term 1, 6.5 section. Okay. That's 6.5. The projective plane. Okay. So where does O go basically, yeah? We need somewhere for O to go. Okay. Okay, so we can very nearly say that reciprocation transforms every point into a line, and every line into a point. The exceptions are the point O, which has no polar, and the lines through O, which have no pole. In case of inversion, we took care of the exceptions by extending the Euclidean plane into the inversive plane. In the present case, we take care of our new exceptions by a different extension into the projective plane. So we postulate a single line at infinity. Postulate existence. So basically we're creating this thing, right? L infinity. Called the line at infinity. Line at infinity, which is the polar of O. Okay? So O goes to L infinity, yeah? And I'm assuming L infinity goes to O, yeah? Okay. And its points, the points at infinity, which are the poles of lines through O. Oh. So these are the points here, right? Points of poles of lines through O, right? Yeah. Which is the polar of O. Poles of lines through O. Yeah, because O lies on these lines through O, right? So the polar of O should pass the poles of all those lines through O, yeah? Okay. The properties of the new line and points are determined by the fact that all the points on a line A reciprocate into all the lines through its pole A. If A passes through O, the polars of its points form a pencil of parallel lines, namely all the lines perpendicular to A. Hence, a point at infinity, such as the pole at A, has to be regarded as the common point of the pencil of parallel lines. So this is the points where the parallel lines intersect now. Okay? Kind of like if you're looking at a road that's going into the distance. Okay? Okay. Such as the pole of A has to be regarded as the common point of a pencil of parallel lines. It follows that the projective plane, there are no exceptions to the statement that any two distinct lines determine a unique point. So A, B determine a unique point. Yeah? So even for parallel lines, now there's a unique point that we should determine. Yeah, so the parallel lines, yeah. Okay. Did we check that L infinity goes to O on this version? And the pole of L infinity is O? I mean, reciprocation. Is that just the definition of reciprocation? They pair up, lines and points pair up. Like the pole of a polar is just the thing itself, right? Mm-hmm. Okay. So in fact, any theorem concerning incidences of points and lines implies a dual theorem concerning lines and points. Okay? Namely, the polars and poles of the points and lines of the original theorem. For instance, we may take the sides of a hexagon circumscribed about the circle omega to be the tangents at the vertices of a hexagon inscribed in the same circle. Does that make sense? You have a hexagon, right? So we have a hexagon circumscribed 1, 2, 3. 1, 2. This is not going good. 4, 5. 1, 2, 3, 4, 5, 6. Yeah. Okay. So if we reciprocate this, yeah. I think we get the same circle, yeah. But the circle goes on the outside now.
Oh, like, no, it means like the points of tangent are like, are the points, are the vertices instead, and then you get something.
Yeah, so instead of being tangent here, right? This is a vertex now.
Yeah. Yeah.
Is that true?
Yeah.
Let me check it. Okay, so remember that? Yeah, so yeah, so this is a 9-degree thing, right?
Yeah.
So if you that's a fixed point. by inversion.
Yeah.
Yeah, so that tangent line now goes to this point. Yeah.
Yeah.
Okay. Yeah. Similarly, these points. Yeah.
Yeah.
Now the intersection of the tangent lines, right? Now go to the join of the contact points.
Yeah.
Yeah. The line that joins these points now is this. Yeah.
Yeah.
That makes sense.
Yeah.
So then you actually get this if you take the reciprocal without so. Yeah. Okay. So this is a cool punchline. Okay. So thus Pascal's theorem and Bryan-Cohn's theorem are duals,
Wow.
and either can be deduced from the other by reciprocation. Okay, so this is Pascal, right? This is Bryan-Cohn.
Yeah.
Put a G there for duals. Do you remember what the theorem was? So this theorem was that the opposite things are concurrent, right?
Yeah.
And then this one was that the lines. Yeah, so it goes across. So you have 3 points, yeah? So you do like that one, and that one. Um, this one, this one, this one, and that one, yeah? And this is coordinate. Okay. So this being concurrent should be dual to this being coordinate. Is that right? Okay, so let's have a look. So we have like A, we could call this capital A, yeah? And B, yeah? And then the dual of this line, AB. Yeah, actually, maybe it's easier just to use the one we already drew it, yeah? Like this point O, right? Is this line O, yeah?
Yeah.
And this point O. Oh wait, no, is this? It's the vertices, right? So it should be like this. Yeah? The current, this is covariant. Okay. So the line joining these two holes should be the intersection of lines. to be the intersection of this strange. I guess I haven't. See, the problem is I don't think I've drawn the lines dual to them. So I think I've done the theorems, right? But they don't correspond.
Yeah.
Yeah. So what would it be? This tangent point goes to this vertex. And this tangent point is this vertex. Yeah, so I think what happens is this line, right? Here corresponds to that vertex, yeah? This vertex corresponds to this line, yeah? So they're gonna meet off somewhere off the page, yeah?
Oh, I know.
Okay. And then this point, so this tangent is here, this vertex here, right? And this could be a triangle. So that's this line here is that triangle, yeah? And then on the other side here, this is the other triangle, yeah? So this is triangle, and then they meet off in the distance again, okay?
Yeah.
And then the last two lines. Square and square, yeah? And then that's gonna be, this is triangle, yeah? So that's square and that's square here, right? So they could meet like here, yeah? And then you get this one collinear line. So it doesn't have to be a convex hexagon, that's kind of, yeah? Like, there's lots of different ways you could do a cyclic hexagon. The Pascal's theorem. Okay? Yeah, so it might be nice to actually write that out properly. If you have the time. Okay. More generally, a Pascal's theorem or Bryan-Connes applied to any circle implies Bryan-Connes theorem or Pascal's for the reciprocal conic. Oh, okay. So in this case, it actually fixes the circle, right? But if you didn't have the circle as the thing, you get a conic. Yeah. So we can now simplify theorem 6.12 by deleting the parenthetic exceptions. Moreover, when we regard this theorem as applying to an arbitrary circle alpha instead of the reciprocating circle omega, we can use omega to derive from alpha a reciprocal conic. Then our constructions for poles and polars with respect to alpha reciprocate into constructions for polars and poles with respect to the conic alpha prime. In this manner, reciprocation with respect to a circle is generalized to polarity with respect to a conic. Theorem 6.12 with the parenthetic exceptions removed. So if you remember that, it was like the secants of the circle can't pass through the center. They can't be the diameters. Okay. Consists of 4 parts which are dual to one another. Therefore, it remains true when the reciprocating circle is replaced by a conic. Wow, it doesn't look like we can get through this whole lesson. In the notation of figure 3.8, the line LM passes through N. Last part of theorem 6.12 into the following direct construction for the polar of a general point P. Okay, let's look at the, you want to look at the diagram? Let's look at the diagram. Okay. Where's N? B times B. P is so what's LM? LM passes through N. Oh, by the way, do you want me to state theorem 6.12?
Yeah, I read it.
You read it?
Yeah. That's all
Yeah, so the pole of any secant, so it talks about the pole of any secant, yeah? Except diameter. Is the common point of the tangents of the secant. The polar of any exterior point is the line joining the points of contact of the tangents. Okay? The pole of a line, except the diameter, is the common point of the polars of the two exterior points of the line. Yeah, so we can say all those things without saying except the diameter. Get rid of that. Yeah? We more regard this theorem as applying to an arbitrary circle instead of reciprocating circle. Yeah, I'm not quite. So the P is not on the conic. Its polar joins the points of intersection. Okay, let's draw this diagram. Let's invest in this diagram. We got D, E, and L. So this is a row line P. This goes to D. This is E, L, and E. B goes to A, goes to L. And EA goes to M. And DB goes to M. B. And so you need this up here. And are these collinear automatically? Uh-huh.
This is L and M.
L and M.
Yeah, but you have to prove that line is the polar.
Oh, okay. So we're giving any point, yeah? What, are we giving any line?
No, given any point not on the point.
Then you construct the polar, yeah?
Yeah.
Okay. So how's it done? So you give this point, yeah?
Yeah, and then you see
Oh, so you draw any two sequence AD and EB, yeah?
yeah.
So you extend them to meet on the line, yeah? So that's L, yeah?
Yeah. L and M.
Oh, so that's how L is defined, yeah?
Yeah.
L is where these two lines intersect, yeah? Okay, and what about M?
And M is where AE and EB.
Oh, okay. Well, I guess you can still take parallel lines, yeah?
Yeah. You can see.
The point of infinity.
Yeah.
Okay, so there'd be the line of infinity too.
Mm-hmm. And then you could prove L and is that polar.
Oh, okay. Hmm. Yeah. We've seen that any pole and polar with respect to a circle reciprocate with respect to another pole, a circle, into polar and pole with respect to a conic. In particular, the center A and L infinity are pole and polar with respect to alpha. Therefore, alpha and O are polar and pole with respect to alpha prime. With respect to any conic except a circle, a directrix. Oh, that's a cool theorem. The directrix. With respect to any conic except a circle, because in a circle,
Yeah,
there's it's not exactly a directrix. A directrix. Maybe the circle has like directrix line of infinity. Yeah. With respect to any conic except a circle, a directrix is polar of the corresponding focus. Actually, there's a lot of stuff to digest here. Like this will take up the rest of the time. Walk times. The algebra is not here. But I don't think any people can absorb that kind of algebra right at the end anyway.
Yeah.
Okay, so how does this work? If you have this secant, right, you find the tangent point. So how does this work? So if you have like a point P, yeah, it's the intersection of AD and ED, yeah. So A yeah, there's something not quite finished about that. Something you need to know something about the pole of A. What do you need to know about the pole of A? Pole of AD passes. So the pole of P, the polar of P passes through the pole of AD. Yeah?
Yeah.
Because P is not on the conic. Notation of freedom. Page 76. Oh, it's just saying dots. The intersection is written by dot. That's what it means. So the LM passes through the intersection of the polars of B and E. Yeah?
Mm-hmm.
Yeah. Okay. And the intersection of the polars of A and D. Yes. Okay, so how can we relate? So the intersections of the polars. Yeah, because AD passes through P, right?
Yeah.
Then the polars of A and D intersect on the polar of P. Yeah. Same with E and B. I mean, what would it be like if you had the sequence, right? You have their point of contacts, yeah? Let me draw it in another color. Black. So if you have B, yeah? D tangent goes there, yeah? the tangent at B intersects here. So that's the pole of BD, yeah? Yeah. The pole of EB is like here, like where they intersect. You know what I'm saying? And the pole of AD is where they intersect. Yeah. Huh? What's that meant to what? So, well, that's how you're meant to find the line LM, yeah? The polar of P. Okay. Now the question is, does M lie on that line? So does the line passing through, I guess this is called N. So this is N. Don't quite have a letter for that one. Maybe O. No, this is L. Maybe L, yeah?
There's another L.
Is it? Oh crap. K. Okay.
So L and K.
L and K, yeah?
Yeah. Will that be the same thing? Like just find the pole of AE in the
Hold on, so the N is the intersection of the tangents from B and E, right? And the K is the intersection of the tangents from A and D, yeah? Okay, so can we show that M lies on that line? So NK.
M is N.
So the polar of EB, right? Okay, so M lies on DB, yeah? M lies on DB and EA, yeah?
Yeah.
So then the pole of M the pole of EA and DB are like here and here. The line joining the poles is the polar of M. I'm confused now. Huh?
No.
And that's the last thing we have, basically. Okay, and then once we've done this, the exercises now all officially make sense because we have the exercises set for even 6.5.
Wait, I meant to do the fixed type of question.
Whatever you want. You should probably do this intermediate ones. Yeah. Okay, let's draw this diagram again. Now that I know where everything's going. Okay, you got a conic. You got any two secants. Yeah. You need a P. And the conclusion is that extending these to that, and that to this, yeah, gives you LM, yeah. This kind of feels like a quadrangle kind of thing.
Yeah.
You have the tangents. Yeah, the tangents are meeting there and there, yeah. That's strange again. So by the 6.12, it's saying that the polar of P should pass through the poles of these two lines, right? And the poles of these two lines are like tangents. Huh? Oh, that's the other one. And then this one is this one. Yeah. Oh. Yeah, I think there's something to figure out now. Yeah. Yeah. And then the exercises that you next week. Like about 10 days from now, I guess. The ones you want me to mark, anyway. You'll probably just hand in some later. Anyway. Yeah, I guess. So I do feel like it is a question of showing that the polar of P, right? So basically the intersection of, the line going through the intersection of the tangents, yeah, is the same as the line going through the intersection of the extended, yeah. these two lines meet at that point, right? That means that the poles go through that point. The line going through the poles of those lines. So it's this line and that line. Yeah, you probably have to go home.
Yeah.
Yeah.